Welcome to the lecture on the calculations underlying ANOVA. In this lecture, we'll start by reviewing the logic behind ANOVA. Then we'll talk about calculating the F ratio being the test statistic that we calculate for an ANOVA. And in doing so, we'll talk about the sums of squares and the mean squares. And then we'll go through the example of hypothesis testing with a one-way between subjects ANOVA, and we'll work through a problem together. So let's remind ourselves what an ANOVA is. ANOVA is an acronym for analysis of variance. And in this, we're going to calculate the F statistic. The F statistic is a ratio of the between groups variance over the within groups variance. In other words, this is a ratio of the variability among the sample means, so differences between different groups that my participants are in, over the variability among the individuals within a sample mean. So we calculate an F statistic when we have 3 or more sample means. So previously we've worked with 1 or 2 sample means, and now we're in a situation where we have 3 or more sample means, and we want to ask a question about whether or not those sample means differ significantly from one another. Because our F statistic is a ratio of our between versus within groups variance, we're going to see that the F distribution is centered around 1 and it's positively skewed. This is because if you have no effect of your experiment, no treatment effect or no experimental effect, your variability among your sample means and your variability among your individuals within the sample are going to be relatively equal to one another. If you have an effect of your experiment, or let's say an effect of an independent variable, you would expect that your between groups variance would increase, and then that would cause your F statistic to be larger than 1. If you have an F statistic larger than 1, that's more likely to be a statistically significant effect. So let's go through an example which we introduced in the last in the last slide. So in this paper, which is a real paper that we're going to use sample data for, we have a situation where people are divided up into 3 groups. They're randomly assigned to being in a control group, a play money group, or a money prime group. In the control group, participants work difficult puzzles, and they know that they can ask for help whenever they want or need it, but they have no other information. In the play money group, they do the same thing, except they have stacks of Monopoly money next to them in somewhere that they can see it. And in the money prime group, they need to unscramble phrases that remind people of money. So the overall question is, if people are made to be more self-sufficient when they're thinking about money, then people in the play money and the money prime group should ask for help less quickly than people in the control group. So let's remind ourselves too that we have factors and levels when we're talking about ANOVA. So the factor is the independent variable that designates the groups or conditions that are being compared. So in this group, the factor is the money exposure or the money condition, and the level is the individual values that make up a factor. So here in this situation, we have control or play money or money primes. So your levels equal the number of means that you have, and your factor equals the number of independent variables that you have. And here's just an overview. We've already calculated our means and standard deviations using statistical software. And visually seeing these data here on the graph on the right-hand side in the figure, we can see the means plotted by the different groups that participants were randomly assigned to. We can see that the mean for the control group, which is 184 seconds, is lower than the mean for either the play money group, which is 305 seconds, or the money prime group, which is 315 seconds. But of course, to see whether or not these means and the spread around the means are statistically different from one another, if these means are coming from populations that are distinct from one another, we need to go through the steps of hypothesis testing. We went through the first 4 steps in the previous video, so if you want to remind yourself of them, go back and watch that one. And we're going to pick up now with steps 5 and 6. So calculate the value of the test statistic, our F, and then stating a conclusion. So note here that these hypothesis test steps are a little bit different to the way that we laid them out in some previous videos, but again, these are just steps in different orders. So let's remind ourselves that our ANOVA is, we use an F ratio to calculate an ANOVA, and our F is a ratio of our between groups variance and our within groups variance. Now we need to introduce some new terminology, because the way that we actually calculate this, the calculation for the F statistic is the mean square, MS, and we have the mean square for the between subjects variability over the mean square for the within subjects variability. So we're going to be calculating these variables in order to calculate the F statistic. So let's take a sort of high-level view of where it is that we are. So we want to calculate our F statistic, which is the ratio of the mean square between over the mean square within. So in order to do that, we need to calculate our mean squares. To calculate our mean square, either between or within, we need to calculate the sum of squares between and within. And we need to put that over, divide by the degrees of freedom for the between or within the variability that we're talking about. In order to calculate this, the mean square, we need to calculate our sums of squares and our degrees of freedom. So to calculate our sums of squares, we actually now are in a situation where we need to calculate 3 sums of squares. So we have our sums of squares for our between groups variance, for our between groups factor, for our within groups factor, and now we have a third, which is the sums of squares for the total. So the total data set in and of itself. And if you look at it, you've seen some variation of this formula before. So this should not be completely new to you, but this is the general framework for what we're doing with the sums of squares. We're going to take our values and subtract some sort of mean value from that, and then square it and add that up. And we also need to calculate 3 degrees of freedom. We have our degrees of freedom between and our degrees of freedom within. We calculated that in the last lecture. So we're going to take for the degrees of freedom between k minus 1, so that's the total number of groups, minus 1. Our degrees of freedom within, so that's going to be n minus k, so the total number of people minus the total number of groups. And we also have a total degrees of freedom. That's going to be the total number of people in your data set minus 1. So there are a few steps to calculate in order to calculate F. There are 9, in fact, 9 different steps. Some of them are a little bit easier than others or more straightforward than others, but ultimately they're all fairly straightforward if you just stay organized. And to help us stay organized, we're going to use this ANOVA table. So you sometimes even see tables like this, an F table or ANOVA table reported in papers. Okay, so let's start with calculating and entering in some information that we're going to need to calculate our ANOVA table. So we've already calculated the degrees of freedom on the previous slide. We remember our terminology, and we've already calculated that our degrees of freedom for our particular study is k minus 1 for between subjects degrees of freedom. We have 3 different groups: the control, the play money group, and the money prime group. So 3 minus 1 is 2. We have 13 different data points that we're going to be working with in this particular data set. And so we're going to take n minus k for our within subjects degrees of freedom. So 13 total n minus k, 3, and that gives us 10. And then we also have our total degrees of freedom, which we have not calculated yet, but that's going to be n minus 1. So we again have 13 people. 13 minus 1 is 12. And you'll also notice here that your degrees of freedom between and your degrees of freedom within should add up to your degrees of freedom total. So you only need to actually calculate any 2 of those 3 measures, and you should be able to work your way back into the third one. Next, let's start by working towards calculating our sums of squares. So let's start with our sums of squares between, and let's just remind ourselves about what the sums of squares is doing, or think about what the sums of squares is doing. So the sums of squares is looking at, it's a measure of our between group means, is about the variance between your different groups. And so I have the 2 different formulas listed up here. They're interchangeable. They're just using different notation. One is the notation from the book, and one is notation which you might find easier to think through or use. But basically what you're taking is the mean for one group, and you're subtracting the overall mean in your data set. And then you're going to multiply that by the number of instances that you have. So for each data point in your particular group, and then you're going to square that. So as the name suggests, the sums of squares between quantifies the variability between the groups of interest, right? So we're interested in the differences between group A and group B and group C, how they vary from one another. Okay, so this is the between groups variance or variation among my sample means. So what this formula is doing, it's subtracting the grand mean from the group means, so not individual data points, and then squaring those variables and adding them all up. So we're going to need our data, which we have here. And then what we also are going to need is our group means as well as the grand mean. So here I have this listed here. So I have each of my group means. So the average time it took people to ask for help in the control group was 184 seconds. The group mean for the play money is 305, and for the money prime, that's 315. The grand mean, the mean of all of those numbers, is 271.6. So now let's start the process of computing our sums of squares between. So let's make sure that we always stay organized when doing this. So first, lay out all of your data like this in one long column. This will help you keep organized. And also, in addition to having the variable that you have, the number for each X, keep also a list of what group each of these variables is in. So my average, my numbers, my data points for the control group are 104, 186, 243, and 203, and I have control next to them. And then for the play money, it's 384, 237, 329, 270, and for the money prime, it's 415, 361, and so on. This is going to be important because, again, we're going to be pulling our means for each group instead of each variable. So we want to keep that straight. So for every data point, we're going to take the group mean that that data point is a part of. So for every data point in the control condition, regardless of the individual value, we're going to take the group mean of 184. This is because, remember, we're now interested in the variability between groups. So instead of taking 104, we're going to take 184. And then we're going to do 184 minus the ground mean. So 271.6. That gives us negative 87.62, which we square, and we get 7,676.5. We do that again for the next number. So 186. Again, we still don't use 186. We use the group mean. So we do 184 minus 271, right? We do this the same calculations as we did above. We do that for the 243, for 203, etc. Okay, so we do this once for every data point in the group, and then we add it up, right? Or what you could do is do this once, right? So do 184 minus 271.62 squared, and then multiply that by little n, right? So you can see that that's listed in here. So multiply that by little n. Make sure that if you do this, you keep your little n's organized, because we don't always have the equal number of participants in each group. So we do this for each group. So we just did this for the control group. Now you do this again for the play money group. So instead of taking 384, I take the average of 305 minus 271, squaring that, and doing that 1, 2, 3, 4 times. And then we again are going to do that for the money prime group. Instead of taking 415, I'm going to take 315, subtract the ground mean, square it, and then do that 1, 2, 3, 4, 5 times, because I have five participants in the money prime condition. So as you can see here, if you just wanted to make this abundantly clear, so because you're taking the group mean for every data point, you can simply take the group mean, subtract the ground mean from the group mean, square that, and then multiply that by little n, the number in that group. But be careful to use the right n for each group. If you do all of that, you should get a total sums of squares for your between groups factor of 44,577. let's take this number and let's add it into our ANOVA table. Oops. So on the next slide, I'll show you the total 44,575.08 and put it into the ANOVA table. But here's just a list, a layout of my calculations for my between groups sums of squares. So now I'm going to take that number, my between groups sums of squares, and I'm going to add it to the ANOVA table, as you can see here. Added it to our chart. Now let's go and let's calculate our sums of squares for our within groups source of variance. So within groups sums of squares, I've written this two ways. One follows the book notation, and I've also included another form of notation, again, in case that makes more sense to you. So now we're talking about within groups variance. And so remember, what we're talking about is the variation among the people in my sample means. So what this formula is doing, it's subtracting the group mean from each individual data point and then squaring those variables and adding them all up, right? So this is my within groups, or a variation within among the people within my sample means. So let's walk through how to do this together. Again, I'm going to lay out my data like this in one long column, also keeping track of what condition each data point is coming from. So for every data point, again, I'm going to subtract the group mean that that data point is a part of. So for 104, that's in a data point that's in the control condition. I'm going to take that number and subtract the group mean for the control group from that. So 104 minus 84, square that. For 186 minus 84, square that. 243 minus 184, square that. 203 minus 203, 203 minus 184, square that. Okay, so I do that one time for each of the numbers in the data points in the control condition. I'm going to do the same process, follow the same process for all of my data points in the next group. So the play money group, I'm going to take that number, 384, and take the group mean of which should be 305. So excuse that typo. So 384 minus 305. And then the same thing for all of the data points in the money condition. So 415 minus 315, which is the money prime average, 361 minus 315 squared, 217 minus 315 squared, and so on. So if I do this, here is a layout of all of the calculations all laid out together. So I'm going to take this, this particular data point. I subtract the mean for that group here. So the 305s, 184s, 305s, and 315s. I have my difference between that, and then the square differences, which I add up. And the total sum of that is 48,234. Okay, so I'm going to take this number, 48,234, and add it to my my chart, my table. So next, if you recall, my degrees of freedom total is just a sum of the degrees of freedom between plus the degrees of freedom within. The same is true for the sums of squares. So my sums of squares total is going to be the combination of my between subjects sums of squares and my within subjects sums of squares. And so that adds up to 92,809. Right? So if you have any two of those numbers, then you don't have to go through the process of calculating the third. You can just walk back into that mathematically. But I'll show you how to calculate the sums of squares total now so that we get a sense for conceptually what it means and how that aligns with the calculations. So when you think about it, the sums of squares total is the sum, again, of the both between and within subject sums of squares. So it's thinking about the overall variance that you have in all of your data set. And so what you do here is you're interested in the combination of those two. So for every data point, you're going to subtract the grand mean from that individual data point. So it's getting a sense for how much each of your individual data points varies from the entire data set. So I have these two different formulas. Again, the top one is from the book that we're using, or that's optional. And on the bottom, I have something that might provide notation that might be accessible to you also. So you take each individual data point and you subtract the grand mean, and then you square that. So for example, I take 104 and I take the grand mean. So that's the mean of all of the means. So 104 minus 271.6, 186 minus 271.6, 243 minus the grand mean, 203 minus the grand mean, and we're squaring all of these values. I do the same thing for for all of the data points, regardless of what condition they're in. So I take 384 minus 271.6 all through 415 minus 271.6, and so on. And if I add up all of the squares of those deviances for those individual data points from the grand mean, I square them and I add that column up, I should get 92,809.08. So here you can see all of the calculations all laid out so you can check your work. And then here is just an overall table listing all the calculations for the 3 different sums of squares in one slide. So we had calculated our 3 different sums of squares, our 3 different degrees of freedom. We have 3 calculations left to go. We have the mean squares and the F to calculate. And the good news is all of these are just simple ratios of the information that we've already calculated. Let's start with our mean squares. So our mean square for between, so our MSB, is going to be a ratio of your sums of squares between over your degrees of freedom between. So in this case, it would be 44,575 divided by 2, and that works out to 22,288. Similarly, my mean square for my within is just a ratio of my sums of squares within over my sums of, my degrees of freedom within. So in this case, 48,234 divided by 10 is 4,823. I have one more calculation to go, and that's the big one, the F statistic, the ratio of my mean squares between over my mean squares within. And so if I work that out, I get 22,288 over 4,823, and my F ratio statistic is 4.62. Now, if I'm going to be reporting this in APA style, I would report this by saying F parentheses, F open parentheses, my degrees of freedom between, which is 2, comma, my degrees of freedom within, which is 10, and then I would report this statistic, 4.62. So lastly, I need to state a conclusion. I'm going to compare, in this case, my critical statistic to my test stat. Alternately, if you have a p-value that you have calculated, you would compare that to your critical value. And so if you remember from the last lecture, we talked about how to find your F critical using an F table. And so you need your 2 different degrees of freedom. That's why we report them. You need your degrees of freedom between and within. And so I'm going to find my degrees of freedom. Sorry, this got messed up. So this is my degrees of freedom between, which is 2, 1, 2, and then I go down to 10. And so my critical F is 4.10. Now I compare my critical F to my observed F. My observed F is 4.62. And so my observed F value is greater than my critical value. And so I can reject my null hypothesis. I can conclude that there's a significant effect of my IV money condition on my DV response time. Or I could say something like the means of participants in the play money, the money prime, and the control group differ significantly. So what information do we have from the one-way between subjects ANOVA test? So we've just rejected our null hypothesis, and by doing so, we implicitly accept the alternate hypothesis. Now let's go back and let's remember what our hypotheses are. Our null hypothesis is that mu1 is equal to mu2 is equal to mu3. Our alternate hypothesis, which we've just found evidence to support, is mu1 is not equal to mu2 is not equal to mu3. So what we've done is we've shown that there's a likely chance that our three different sample means are coming from different populations. So we know that there's a difference somewhere among those different sample means, but we don't yet know which of those means differ from one another. In other words, although we've hypothesized that participants in the play money and money prime group are going to be wait longer to ask for help compared to participants in the control group, we haven't yet found support to confirm or deny that, right? To be in support of those hypotheses specifically. We've just simply found that among these three sample means, there's a difference somewhere. So determine which means vary from one another significantly. So which of those three different groups vary from one another at a level of statistical significance? We need to go and conduct post hoc tests. We'll cover that in the next lecture. But in sum, here is a sample source table, sample F table, or sometimes it's called a source table. And this lists out all of the different formulas that you would need for your calculation.